All right, hello back. Time to talk about electrocyclic reactions. All right, so as we talked about in the previous video, your regular Diels-Alder reaction, you could perform them under thermal conditions, but you could also perform them under photo-induced conditions, and the end results for the cycloaddition product differ depending upon what kind of condition you're doing the reaction under. And here, there'll be no difference in that respect. We will see different outcomes depending upon whether the conditions are thermal or photo-induced. So now we're going to kind of change the amount of pi electrons we have. And by the way, the difference between a Diels-Alder reaction is that we have two different molecules reacting with each other, whereas electrocyclic reactions, it will be the same molecule reacting with itself. And not even two different molecules of the same kind. No, we're talking about one molecule reacting with itself. So for instance, if we're talking about a diene, that has 4 pi electrons, and this is the only thing you have present, you can still heat this up and undergo a reaction. Now, the reaction that you end up doing creates a ring. Now, this ring, since it only involves 4 carbons that are conjugated, you only get a 4-member ring. And you still go based on what the orbitals are doing. But this is a reaction that's happening on itself. So basically, carbon 1 and carbon 4 are becoming bound to each other covalently in this reaction. And if you consider the pi electrons, the molecular orbital electrons, here is only this molecule that we have to consider, but we still need to look at the HOMO and the LUMO, or at least, to some degree, the frontier orbital. So if you look at the 4 pi electron system, we only need to utilize the first 2 molecular orbitals to account for those 4 pi electrons. And if you think about the idea of actually interacting carbons 1 with carbon 4, then the idea right here is that you could look at the HOMO. You could even do this with, the LUMO if you wanted to, but you could look at the HOMO and then the idea is pretty much this. You want to rotate the left side and the right side to bring the same type of a lobe of the p orbital towards the middle of the molecule. So if we look carefully, based on the HOMO orbital, we have an orbital is pointing up right here. We have an orbital is pointing down right there from the point of view of the shaded region. So one way to bring them closer together is to have the one on the left rotating clockwise so that the shaded lobe is pointing into the middle, and then have the right side rotating also clockwise so that you have the shaded lobe that's pointing down here, going towards the middle section. And that will allow you to form your single bond right here. But because we're doing those rotations, once again, we end up changing the orientation of methyl and hydrogen, right? So the methyl will come closer to us, end up on top of the hydrogen. And over here, the ethyl will end up being pushed down. Therefore, the methyl will end up above the ethyl group. And that is the regiochemistry that we're seeing happening right here in this cyclobutene ring that is forming. All right, so because the rotation is happening in the same direction on both sides, this is a conrotary rotation. Now, if we look at 6 pi electrons and we stick to these thermal conditions, we're basically talking about a triene, right? So something like this, right? This is technically 1,3,5 heptatriene. And then you have a fluoro group in there for good measure, right? So technically 1 fluoro, 1,3,5 heptatriene. But in a 6 pi electron system, because you have 6 carbons that are conjugated, you will end up making a 6-member ring. And then by now you have probably already noticed this. The number of pi electrons that you start with in the acyclic molecule, you end up with 1 less in the cyclic one, right? Same story right here. We start with 3 double bonds in the acyclic molecule, and we end up making a cyclic molecule that has 1 less pi bond. All right, so if you consider the molecular orbitals of the 6 pi electron system, that means we have 6 molecular orbitals to deal with. 1 The first one is fully in phase. The next one that is out of phase once, through the middle. The third one that is out of phase twice, through carbons 2 and 3 and carbons 4 and 5. And by that time, you have gone through 3 molecular orbitals, so that accounts for all 6 pi electrons. So this orbital right here is the HOMO. And if you look at the extremes on the left side, you have shaded region on the top, and over here on the right side, you have the shaded region on the right side as well. So if you look at that, kind of like draw it, so it's somewhat in the same vicinity. And then notice that the fluoro is pointing, below. The methyl is also pointing below. So when you draw them this way, the methyl and the fluoro should be pointing in the same direction, right? And then the hydrogens that are also present in there will be pointing in the opposite directions. Okay, so in this scenario, the p orbital on the left has the shaded lobe on top, and the shaded lobe on the right side of the molecule is also on top. So here, to make them come together in the middle, you have to rotate the left side clockwise while you rotate the right side counterclockwise, right? That will bring the shaded lobes together. And if you do that, the fluorine will end up on top of the hydrogen on the left side. And right here, the methyl will end up below the hydrogen on the right side, right? And that will basically give you a 6-member ring, which will account for the regiochemistry that you're seeing on the molecule over there. So obviously, there's a lot of things happening here, but I want you to notice that when you go from 4 pi electrons to 6 pi electrons under thermal conditions, the rotation changes, right? It's conrotary for the 4 pi system, whereas it's disrotary for the 6 pi system. And you might guess that when we switch over to the photo-induced conditions, we're going to see something similar happening, right? In the 4 pi system, once again, we deal with the 4 molecular orbitals, but this time around, 1 electron from what used to be the HOMO orbital is promoted to the previously known LUMO orbital. But now that makes this orbital the HOMO orbital, the one that we based the premise on. And here you can see that you got the shaded lobe on the top on both left and right portions of the molecule. So when you do this thing, the way to bring the shaded lobes in contact with each other is to rotate the left side clockwise and the right side counterclockwise. So in essence, it's a disrotary rotation. And what I will do is place the methyl above the hydrogen, and here on the right side, it will place the ethyl above the methyl, okay? And giving us the proper regiochemistry that we see up there. And then switching over to the 6 pi electron system, you might have already guessed it. We're going to be dealing with conrotary rotation, because when you look at the orbitals, all 6 of them, right? By the time you get to the third one, you're dealing with the original HOMO, the ground state HOMO orbital, but you promote 1 electron to the next orbital under photo-induced conditions. So this becomes the active player in the cyclic reaction, the electrocyclic reaction. And if you look at the left side of the molecular orbital, shaded orbital is on top, whereas on the right side of the molecule, the shaded lobe is pointing below. So as far as addressing the situation right here, so that the shaded lobes end up pointing towards the inside of the orbital or the molecule, you have to rotate the left side clockwise. And for the right side of the molecule, you also need to rotate that clockwise so that you bring the shaded orbital below into the middle. So what that will do is it will raise the fluoride above the hydrogen, and it will raise the methyl above the hydrogen. So you will have this exact configuration, which accounts for the regiochemistry you're seeing right here. So pretty much in summary, if you're looking at thermal conditions, from 4 pi to 6 pi, you go from conrotary to disrotary. If you're looking at photo-induced conditions, from 4 pi to 6 pi, you're looking at disrotary to conrotary rotation. And one way that sometimes I use myself to kind of help me remember this is, I mean, this is kind of silly, but CD DC, and I haven't thought of a mnemonic to, to go along with that, but at least CDs in DC, that might help you out. And it kind of works also if you just compare 4 pi to 4 pi and 6 pi to 6 pi, because you go from CD to DC. So it kind of works, going left to right or top and bottom, as long as you kind of keep this as a table format. But that might help you kind of get to the point, because especially if you're doing a lot of these type of problems, it will become kind of inconvenient to have to draw all of the orbitals every single time. Like, do it once, do it twice, that's okay. But if you have to do it like 10 times, yeah, that's going to take a long time to do the problems. But if you have knowledge already, prior knowledge that yes, if the system is it's a 4 pi electron system, and you're doing this under thermal conditions, then it will have to be a conrotary rotation. So you just go ahead and do that instead of having to deal with the orbitals. So this might help you out. And that will bring us to the last portion of this lecture, which is the spectroscopy portion. And we're going to save that for the next video. So I will see you there.